anyone know a game where it's a good thing to roll a 7? Perhaps 7 or 11, very good things to roll. What is so special about the 7? Okay. So we're going to work through this problem together, make sure that we can think about it correctly. So you toss 2 fair 6-sided dice. Find the probability that the sum is going to be 7, and B, find the probability that the sum is going to be even. How would you do this? People actually solved it already, but what did you do? Yeah?
I just counted the possible ways you can get 7.
Okay.
I was going through 6 times.
So, what did you actually do here? Sorry, one solution.
I did 1 plus 6, 2 plus 5, 3 plus 4.
Oh, so you enumerated. Okay, so our sample space is the set of all possible pairs, right? So you could have a 1 and a 1, or a 1 and a 2, or a 1 and a 3, like a 2 and a 1, or . So we have all possible pairs. And you actually just listed all of them. How many ways can we get to a 7?
6
6 and 1. 1 and 6 is another possibility.
2 and 5.
2 and 5. 5 and 2. 3 and 4. 4 and 3. Anything else? That is it. Now the question is, so you just thought of how we're going to think of the sample space, and what is the size of the sample space? 36. Why? Because we're counting tuples. There are 6 options for what to go. It's the amount of things that have where there are 6 choices here, and there are 6 choices there. This is counting tuples with repetition allowed. So that gives us 36. And the size of A, as you can see here, this means the probability of A, the probability of actually rolling a 7, is going to be 6 divided by 36, or 1 over 6. What about B, sum is even?
Yeah. Couldn't you do a chart here as well?
But we didn't do a chart before.
Okay. So
He literally enumerated, he listed it. Maybe we can talk about another way to look at that same problem, and then we'll see which one we'd like. Another solution. We could have done that chart that we mentioned before. And the nice thing about the chart is it allows to answer a lot of other questions in the same breath. So let's say here's die 1, here's die 2. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And the focus here is the sum of the dice. So here it'll be clear that there will be 36 possibilities because we have a 6 by 6 square of possible values. And what you would do is you just write the sum in each thing, right? So 1 plus 1 is 2, 3, 4, 5, 6, 7. This will be 3, 4, 5, 6, 7, 8. This will be 4, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, and 7, 8, 9, 10, 12. So we could have started by writing out that chart, which is a nice way to actually see all the possibilities. You can list them all. And now if we look at A, probability of what we are going to do is that we saw that the total number of possibilities, that's the size of my sample space, but here I can see that that's 36 right off the bat. Now what I want to do is the number of ways to get 7. And what we can do is we can literally go and we can count them. So there's 1, 2, 3, 4, 5, 6. There's 6 ways to get a 7. So now, probability sum equals 7 is going to be 6 over 36. So you can do it that way as well. 1/6 is the actual answer. The nice thing about doing it the chart way is that I can also answer a bunch of the other questions at the same time now. Right? So I can look at B, probability that the sum is even. Circle those guys in blue. What are those guys? Well, it can be 2, or it can be 4, or it can be 6, 8, 10. So if you count all the blue circles, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there are 18 ways to have an even sum. This means probability sum is even. 18 of 6. So that would be that probability, which you could reduce, but whatever. Moving on to the next question. So someone takes 2 dice, they roll it once. What would you, if you had to put money on it, what would you put money on the sum being? Now, there are quite a few ways to do this, and this is kind of giving a hint or a kind of foreshadowing to something that we would call a probability distribution. But basically what you would do is you would write down what is the probability of all the possible sums. At least that's what you would try to envision. So we know all the possible sums, they range from 2 through 12. So then I would kind of think about, well, what is the probability of the 2? What is the probability of a 3? What is the probability of a 4? What is the probability of a 5? What's the probability of a 6? What is the probability of a 7? What is the probability of an 8? What is the probability of a 9? What is the probability of a 10? What is the probability of an 11? What is the probability of a 12? So you will notice from the table there's only one way to get a 2. There are 2 ways to get 3s. There are 3 ways to get 4s. There are 4 ways to get 5s. Count the 6s, there are 5 ways to get a 6. There are 6 ways to get a 7, we already counted that. But now what you realize is that 7 is along the main diagonal. That's going to be the longest string of numbers that you have. Once you move down now, you actually start counting down. So this is going to give us a 5 out of 36, a 4 out of 36. It's going to go right back along the main diagonals. So now, what you will notice here is that the 7 is the most likely outcome. Now that's only 1 out of 6 chance, but that compared to any other number, that's going to be the best one. So, another way to look at this is to draw what we call a probability histogram. Where basically you are going to sketch the probability versus the possible outcomes. So, one outcome is a 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. And what you can do here is you can just draw a bar on each of these guys that counts the probability. So we have a 1 over 36, a 2 over 36, a 3 over 36, a 4 over 36, a 5 over 36, a 6 over 36. The 2 is a 1 out of 36, the 3 is a 2 out of 36, the 4 is a 3 out of 36, 5 is a 4 out of 36, 6 is a 5 out of 36, 7, so these guys are all slanted, 6 out of 36, then you'll notice it starts to come back down. So when you actually sketch it out and you write these bars that represent probabilities, it is clear that the bar over the 7 is going to be the most likely outcome. Get a lot of things, and we'll be revisiting this idea, the idea of listing all the probabilities and sketching them out. We'll get back to that when we talk about probability distributions. But these are just some ways you can analyze a problem in terms of its probabilities. And you'd also notice that if you were to say, for example, now if we want to look at this and talk about the probability of the sum being even, we know we care about the 2, the 4, the 6, the 8, the 10, the 12, and what we can do is we can actually add the probabilities. 1 out of 36 plus 3 out of 36 plus 5 out of 36 plus 5 out of 36 plus 3 out of 36 plus 1 out of 36. We'll get 18 out of 36 using axiom 3 of the probability, because these guys don't overlap. Now here's something I do want to mention though. Maybe I'll mention that after something. find the answer without listing? I mean, you can easily draw the table, I understand, but what if there were so many options that you wouldn't want to draw anything out? You wouldn't want to actually create a table. How would you be able to do the same problem without listing anything? How would you think about it? Yeah?
Would you try to find a union?
How would we do that? We don't know anything about the information. We're back at the very beginning. All I know is someone's rolling 2 dice. How do I know the probability that the sum is going to be a 6? Or the probability that both will be even, or something like that? Can you get to that answer without listing? Think about it. Maybe try to come up with another way. Here's what I don't want you to do, though. Because usually a lot of books, they start out with this example and then they do something crazy like, what if there were 4 dice? And then things start getting really crazy. It gets crazy with 3, actually. Just with 3 dice. If you kind of do this kind of analysis with 3 dice, it's hard to draw out the table because you'll actually have like a 3-dimensional table, right? The third dice would be like a line of 1, 2, 3, 4, 5, 6 coming out of the board. There will be 6 times 6 times 6 total possibilities. That's a lot. And then it starts to get a little bit more complicated. Then you have to be a little bit smarter on how you're thinking of the possibilities, right? But for 2, it's not so bad. You can actually draw them out. You can list all the possibilities. You can get away with a lot of stuff when the numbers are small. When they start to get large, it's a problem. Here's what I don't want you to do. Here's the wrong way to do the problem that I've seen several times before. So we're going to look at a wrong way to do the problem, and you're going to tell me what's wrong with this way of doing the problem. Okay? So here's something I've seen. So a student decides to, okay, let's look at the sample space. I'm going to list all possible outcomes. Well, the sum can be a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, a 10, an 11, a 12. And what is the event that I want? Well, I only want a 7. So this means the size of the sample space is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so that's 11. The size of the thing I want is 1. And so this means that the probability is 1 out of 11. Why is that the wrong answer? Do you guys understand the reasoning that I was doing? Like, I've seen that reasoning. What is wrong with this reasoning? Yeah.
A lot of the numbers repeat, so you're not accounting for the other 25 numbers.
Right. So you want to remember the problem is, so this is the wrong way to do this. This is not the correct way, so just so you know. I just want you to be thinking very carefully about these things. I want you to remember that that formula that I gave you, where you just divide the sizes of the sets by the sizes of the sets. Remember, to use the probability of A equals size of A over size of S idea. S must list equally likely outcomes. And as he said, there are numbers that repeat. So yes, you list the 7 one time, but this actually occurs 6 times. Right? Whereas, yeah, you list the 2, but it actually occurs 1 time. And so on and so forth. So this list doesn't really represent an equal likelihood type of list, right? Because some of the members in the list, they actually show up more often than other members in the list. So this wouldn't be, at least if you're using this kind of equation, this wouldn't be the way you'd want to set up the sample space. You definitely want to make sure that when you're using this equation, your sample space has equally likely events. Everything you write down in the list, they all have the same chances of being chosen. Here, the 7 has a greater chance of being chosen than the 2, so writing this down as our sample space is not good enough for this equation. Now, there are other ways you can do probabilities where you list things and you know that not everything has the same chances, but then you have to talk about probability measures and weights, and probably don't want to get into that. Usually there will be a way for the kind of problem that I give you to actually list all possibilities or conceive of all possibilities so that there's going to be an equal likelihood for each possibility. So don't fall into that trap. Be sure that when you're actually setting up the sample space, that you list things such that any one thing is going to have the same chance as any other thing of being chosen. Let's look at something that was on the probability teasers handout. See if we can actually reason through it now. So example 2. Got a lot of mileage out of example 1. There are 4 playing cards. Two red, 2 black. Pick 2 at random, so you're not looking what you're picking, you just grab 2. What is the probability that both are the same color? This one I also want to look at multiple ways to do it. Someone tell me one way to do it. Yeah?
Could you do 1/2 times 1/3?
By what mechanism?
Is the probability of like picking a red card would be 1/2, and then once you pick that red card, probability of picking another one would be 1/3.
That's the wrong answer.
Okay.
Try to set it up based on principles taught in class so far. Yeah.
Like where we enumerate the choices. So like
So you list them out? Okay.
yeah,
So
like, red,
your sample
red,
space, what do you think?
red. Right?
Red?
Yeah, red. And then red, black.
Oh, so you're listing as tuples.
Yeah.
Okay, so that's going to be different. So
Oh, okay.
let the cards be. So once you're doing tuples, order matters. You're going to distinguish between the cards. Let the cards be red 1, red 2, black 1, black 2.
Yeah.
Okay. So there's 2 reds. I'm actually going to list all the possibilities. So now I'm conceiving the sample space as tuples. So it could be red 1, red 2. Could be red 2, red 1. Could be red 1. But let's list it in a more well thought out way. Let's look at red 1 and deal with all the possibilities for red 1. So I could have red 2. I could have black 1. I can have black 2. I can have
And then you start with red 2,
red 2.
red 1.
Okay. There's going to be a bunch. What do you actually want? Can you list all of those? Yeah.
I have a question. Why does order matter here?
It doesn't necessarily. This is one solution. The way she started to say to me the problem has order inherent in it.
Oh, I thought it was just 4.
Why is it just 4?
I thought it was just like red, red, and then red, black, black, red, and then black, black.
Well, that's another way to do it then. Let's continue with this version of the solution because you can get to the answer this way. That's kind of what I want to show with this problem. Multiple ways of looking at the same thing. Different people might look at it different ways, and I want to show how the correct reasoning would go. So following this reason, I pretend order matters. I distinguish between the red cards and the black cards. All possibilities would be listed like that. What would what I want look like? Yeah.
Red 1, red 2, red 2, red
Or
1.
red 2, red 1. So 2 reds, vice versa. Yeah.
Black 1, black 2, black 2, black 1.
Okay. Now here comes the hard part. What is the size of the sample space? Yeah.
4 choices times 3 choices is 12.
Sure, it's 4 choices times 3 choices because you have 4 things that you can pick here, and then there'll be 3 things that you can pick over here. Now this is going to be 4 choices times 3 choices. By the way, I want you to appreciate that that is P of 4, 2. How many ways out of 4 things can I choose 2 things in a certain order? So that's going to be 12. What is the size of A? Well, it's 4. Like I can literally
It's
list it
4.
here. Right? So this means the probability is going to be 4 over 12. It's actually 1/3. So don't worry, eventually, I think towards the middle or the end of next week, I will teach you the circumstances under which you can multiply probabilities, so you can do a kind of process like Christian was thinking about, but that wouldn't work here. The 1/2 times the 1/3. Under what conditions can you multiply a probability to find an answer? Like I haven't told you about that yet. You need something called independence, which I have to tell you about. That's one way to get to the answer. The answer is 1/3. Now, here's another solution. Suppose order does not matter. And someone in the other class made a mistake that I mentioned. I don't remember if someone in this class actually made that mistake, but chances are you did. That I'll mention with this example in mind. So let's say order does not matter. This means I would not think in terms of coordinates where the first and the second position actually matter. I would think in terms of sets. I would say I don't care what order they show up in. Think of my sample space as a set of sets. So I can put a red 1 and a red 2. And I don't care if the red 1 is listed before the red 2 or not. Right? Or I could list a black 1 and a black 2. Or I could list a red 1 and a black 1. Or I could list whatever. So there'll be a bunch of things here. And the thing I want is going to actually now only be 2 things. In this conceptualization of the problem, there are only 2 things I care about. 2 R's or 2 B's. I don't care about the order, so there's only really 2 things I have to list. And now the question would be, what is the size of S? So this means how many sets of size 2 can I create from a set of size 4? C4, 2. 4 choose 2 random ones. I don't care what order. So we'll worry about what that is. What is the size of A? Now here I can see that it's 2. And so here, the probability of A will be 2 divided by C for 2. Do you know what C for 2 is? It is actually 6. So C for 2 is 4 times 3 divided by 2 times 1. And if you do that, you also get a third. Moral of the story. There are times when you can think of a problem as having order, and times when you can think of a problem as not having order. The important thing is you do not mix the two. I think in yesterday's class, I was doing that poker hands example, and we counted the cards, the all possible 5-hand cards that you can get with 52 choose 5. And then I asked the question, well, how can you get a full house? And the student said, oh, well, you know, you can have 52 choices, then you have to choose another one of those cards, so it's 52 times 1, then you have to do that. The problem with doing that is that they counted the sample space one way using a combination, and then they started counting the thing that they wanted another way using permutations. You don't want to mix the two. Meaning there are times when you have the options of thinking of order or not order, just what comes easier to you, but it's very important that you are consistent throughout the problem. Once you make the choice, I'm thinking tuples, think tuples throughout the problem. Don't think tuples in one part and then think combinations in another part, because once you start mixing them, that's going to be the bad idea, right? So if I were to get that is the size of the sample space, and then I think about this as the possibilities, I would get the wrong order. Or vice versa, if this is the size of the sample space, and I think of this as the possibilities, that's going to be the wrong order. And the thing is, that mistake is actually easy to make because most people don't actually write these out. They kind of think in their head. Oh, I'm kind of imagining that that's what happened. But the thing is, you can't really hold that thought of exactly what the set looks like and then be figuring out a problem over here. It's actually hard to do in your head. So you actually lose some information. So it's really nice, even if you don't list everything out, like here I put ... be sure that you know how you're thinking of all the possibilities. Write it out. Okay, I'm thinking of it as a coordinate, or I'm thinking of it as a set of sets, or I'm thinking of it as by this table I drew. However you want to think of the possibilities, be very careful how you list it out, make sure you fully understand that. Then you can start figuring out, how do I get subsets of that thing that give me what I want? So there are times when you do have the option. Now, to be fair, there are times when thinking in order versus not order, one can be way harder to pull off than the other one. But in general, you kind of have an option. Like, I can think in terms of order or not. Sometimes the problem is given to you where the order is just automatic. It's just, okay, it's better to think in terms of order, because to think out of order is just going to make it a lot harder. So I just wanted to show you that you do have options. So there isn't only one way. The goal is just make sure you are consistent. You are setting up your sample space in some definite way that you know about, and you are consistent with that line of thinking throughout the whole problem. Make sure that the way you list your sample space has all equally likely events. Like any one of these coordinates is just as likely as any of the other coordinates that appear. And then you can go through the problem. So to end, I want to kind of talk about another example that's going to lead us to a different kind of probability, which is on the way to the situation where we're going to multiply probabilities. Example 3. I'm just doing multiple variations of each example, depending on what example. Okay. Here, you roll a 6-sided die. It's fair. About 2. So the same as the first situation before. What is the probability? The sum is 10 given that a 6 was rolled. So let's look at this situation. 2 dice are rolled. Now, I tell you, so let's say you don't see the dice, right? You're blindfolded or whatever, and I tell you, oh, one of the dice is a 6. If you had to guess that the sum was 10, what are the chances you would be right? So let's actually look at this, how we're going to be doing it. Let's say here, my sample space, I'm thinking of it as that table, so a list of coordinates. You know, so I could have a 1 and a 1, or a 1 and a 2, or blah, blah, blah. We know that there are 36 things in here. Now, let's look at how many ways possibilities for 6, possibilities for sum equals 10. What would that list look like? This one is easy to list. Yeah.
6, 1, 4, 6.
You can get a 6, 4. You can get a 4, 6.
A
No?
5, 5.
5, 5. Any other possibilities? Yeah, I know, but just what are the possibility that the sum is 10? Let's take each of these things separately. We have the sum is 10 and a 6 is rolled. How many ways can the sum be 10?
It's 5, 5 twice.
No. So, those are the possibilities. Now, if I were to look at, call B, the set that possibilities where 6 is rolled.
Why would it be 5 do twice? Because if it's a 2-hole, wouldn't there be 2 choices?
The first dice versus the second dice.
There's only 1, 5, 6, 7, 4, 6.
It's like,
Or are you saying like the 5, 1 and the 5, 2 kind of thing?
No, I'm just doing 5, 5.
Okay.
Possibilities where 6 is rolled. What would it look like to have a 6 rolled?
3, 3.
No, like literally
Like
the
a
6
six.
is rolled.
2. You could have
So
6, 2.
you can have a 6 and a 1, or a 6 and a 2, or a 6 and a 3, or, well, that goes all the way up to a 6 and a 6. Or you can have a 1 and a 6, a 2 and a 6, a 3 and a 6. 6 and 6 is the same. So this goes up to 5 and a 6. So now let's think about this problem. So if someone tells me, okay, 2 dice are rolled, right? I'm thinking, okay, what are all the possibilities? There are going to be 36 of them, right? Now they tell me, oh, by the way, one of them is a 6. What would you say now?
Your sample space should go.
Sample space just switched. This is no longer the sample space. When told a 6 is rolled, B becomes the sample space. So this was the issue that happened with the 2 girls problem, or even the Monty Hall problem. When I tell you one of the children was a girl, your possibilities now change. Your sample space switched from this to that. Now, here is going to be the question. How would I find the probability that this is my new sample space, that the sum is 10? What you're going to notice is that the 5, 5 is not in here. Right? There's no 5, 5 in this set. What does that mean? So this means
2 over 4.
if I look at the set A2, where the possibilities exist that a 10 is rolled, given that this is the new sample space, now that's only 2 things. Now, I want to find the probability that sum is 10 given 6 is what? Now, the denominator is going to be the size of b as opposed to the size of s. And what is the size of the set that's going to be the numerator?
A2.
Yeah, but can you tell me as a set?
A2.
What is how can I describe A2 based on these two situations? So now that's not a situation.
A is a subset of B.
This is not a subset of that. But if you were to describe this set using these two, it's right there. It's one of the sets thing.
It's the overlap. You know?
It's the overlap.
Yeah,
It's A intersect B.
that's what I meant.
Right. I need to know, these were all the possibilities when everything was on the table. Once I throw away some things on the table, now the only possibilities in here that matter are the ones that intersect with the new sample space. This guy no longer matters to me because he's not in there. So that would be the correct way to do the problem. Now here's this thing that the sneaky math people always try to do. They divide by something very convenient. In this case, let's look at the size of the original sample space. This ends up being, well, that's the probability of A and B. It's divided by the probability of D. This is a new type of probability. It's called the conditional probability. The side over here is going to be called the probability of A given B. And this is how we're going to compute it. We'll talk a little bit more about that tomorrow, I guess. We're out of time.
I'm so mad.